Okay, welcome back to information storage and retrieval. We have covered some different structures for building an information retrieval system. And today we're going to talk about the efficient ways to use our most recent structure, the inverted index. So, Boolean queries. We've touched on these already, but we're going to revisit this, make them a little more solid. So remember, we are dealing with this world for information retrieval systems. We have an information need from a person, a user. We have some worldly set of unstructured data. And then ultimately we want to merge those into our search results, right? We are trying to, this is a monumental task. I always talk about how Google is doing it constantly. There's a reason Google is so powerful these days. They've been optimizing this incredibly difficult task. So, what is Google? Who's in the middle? We build information retrieval systems. Okay, so let's recap. What's the general flow? Each one of these steps we'll cover in more detail at later dates, but the hope is that you get the general idea of how they work first. So, first, from the wide world of all unstructured data possible that lives out there, first we have to select some kind of collection. We are looking at a set of documents. Remember, documents being anything, not just text, not just what we think of as sheets of paper in folders or whatever. It's anything that has information in it that's worth looking at. Could be a video, could be music, could be text. It's often text. Text is the easiest to do these processes to. So first we collect all of our documents into one spot, and then we tokenize them. We go through them and cut them up into processable chunks. Then we normalize them into terms. Okay, so we turn all this raw, real-world text and other chunks of documents, but we focus on text for now. We turn them into things that can be more easily a good touchstone, right? We turn them into keys so that if I want to come in with a query, a search query, it can also get broken up into keys and we can find the overlap. So on the other end, we have our information need comes usually in the form of a query in a search bar, right? Abacababab, right? We do the same kind of process to those queries. We turn them into tokens, so abba, kaba, and a bab, and then we normalize them so that we get rid of some of the superfluous information. And now they are in the same terms, right, as the documents are. So we have pulled all the documents down into these terms, and we've pulled the query down into these terms. And now we're going to use an information retrieval system in between them to find the documents that contain our answers to our information need, right? Initially, we used the term document incidence matrix. This one was very straightforward. We just would say, hey, for every document, does this term appear in it or not? So term A might appear in just documents 2 and 3, B, etc. Then, when we were using this, query processing was straightforward. We would just say, okay, these are shorthand, so we're going to find ABBA and KABA, which documents have A and C, okay? So we would just do the top to bottom Boolean check. No, yes, great. Okay, so those two documents have at least those two, and then we'll also pull out B and check there. Okay, so only the last document. This was the way we initially approached search results, and it does it. It successfully does it, right? But there were some issues with these kinds of matrices. As far as being efficient, they weren't especially, was the problem. They would grow far too quickly, and they are sparse. There's not much information in them, and you can't break them up and store them separately. You just have to have all of the information at all times available in memory. Not great. when you're trying to build a system that is very flexible. We've gone with a different structure. So last time we talked about how do we compile the same kinds of terms, right, into a better structure. And we came up with the inverted index. It has a dictionary of terms, and for each of those terms, a list of postings of the document IDs where those terms live. So now that brings us up to speed. So now we've got to ask, how do we process queries using this new list-based structure? It's not these big, although large, but very clean and easy incidence vectors, right? Now we have to ask, what do we do? What processes do we need to use to make query processing of an inverted index postings list quick and straightforward? So let's talk about ways to process these Boolean queries. So now we're in the inverted index world and we want to use it, right? But those nice, clean bit string Boolean operations just don't work on lists. Lists can be of any length there, and they're not fixed. There's no guarantee that things will line up, right? They're just a sparse little list, and we want that. We still need that, because if a term only appears in 30 documents, we don't want it to be a million rows long. So when we compare the instance matrix vectors, it's very easy, as we looked at last time. We just do the bitwise Boolean operation across each item. But the issue, as we looked at before, is that lists, you got to do a lot of comparisons to rule things out. You had to compare each item in this list, in list A, to each item in list B. That's not ideal. So today we are in search of a way to make these postings lists operations quicker, more straightforward, less bloated in terms of processing. So that will do. So three topics to get into this. First, we'll talk about the basics of set theory. This is just another way to think of Boolean operations, but because we're no longer just doing literal binary comparisons, we'll talk more about sets in general. And then performing the operations on these postings lists, and we're going to talk about one specific algorithm that is the most efficient and exploits some things that we've already done, i.e. the sorting that we've done. Makes some things very straightforward for us. Thank goodness. So, set theory. We can think of the postings lists, instead of thinking of them as these like rigid structures, they're just sets of items that belong to one term has one set of documents associated with it, and another term has another set of documents associated with it. So our postings lists are sets. What can we do with sets? Well, the answer is we can do the same things that we could do with Boolean operations, but we call them something different. So first, intersection. This is the same as and. So for two terms that have a different set of documents associated with them, set A and set B would be the intersection. Only the overlapping documents we would pull out. This is the fundamental process of processing a query. Usually we're looking for and. Sometimes we add in ors or nots and things like that, but by and large, anytime you just from the hip type something into Google, it's a lot of ands. I want something that has this term and this term associated with them. So intersection will become a very fundamental piece of what we do. So we do the intersection and. We can also do union, which is or, similar to the same idea. So sometimes we want to expand terms, right? We want to be able to say, well, I want this term, but either of these other two terms will suffice. So we want to expand the search to include both of either of those terms. So or is the union of the two sets, right? So the overlap, and the unique items. Finally, another common one is not. So this is called the complement. I want everything that is not in this term. So if a term is associated with a set of documents, I want to exclude those documents and make possible all other documents, right? Everything except A. So these are the three basics, and very similar to the Boolean operations we've looked at in the past. So let's look at each one. Remember, everything from both sets is intersection, and it uses this little upside down U, this sort of an N-looking shape. So that's the operator. We will have intersection, and it takes two sets, right? So A has documents 1, 2, 3, and 6. B has documents 3, 5, 6, and 8. The intersection of these two, the overlap only, would be, if you use your human eyes, you can see pretty quickly, just 3 and 6 are in that set, right? So the A intersection B, the intersection of A and B, these sets, is 3, 6. Okay. Now, union will be sort of the opposite. So anything from either set. Okay. So U, the operator, the right side up U, or just get used to union and intersection. These are common terms. So as with intersection, it takes two sets, and we're going to return anything that is in either of these sets. So again, A has 1, 2, 3, and 6. B has 3, 5, 6, and 8. So not only are we going to get the overlapping parts, 3 and 6, we're also going to pull out 1, 2, 5, and 8. We get all of them. Everything from both sets, from either set. Finally, we'll look at complement. Everything not in the set. Okay? So, great. Here's it. And this one is interesting. It only takes one set. You don't have to... This works without a pair of sets. So just given set A, it takes one set. So let's say the whole collection has IDs 1 through 10. And set A has 1, 2, 3, and 6. Well, not A is 4, 5, 7, 8, 9, and 10. Right? So these are useful. These are the ways that our search terms can interface with the full collection. Right? Our term will come in and say, hey, what are the documents from this term? What are the documents from this term? So we achieve the same basic ideas we did with the term incidence matrix using set operations for these sort of loosely defined sets of items instead of the more precise and straightforward list, the comparisons of the vectors of incidences. So now we're going to keep digging in and try to implement these. I want to show you how we can do these optimally. Mostly we'll focus on intersection since, again, a lot of search is narrowing down. Less of it is about expanding. So how do we perform some set operations on postings lists, right? We are pulling down these lists and we're going to filter them to say which items exist in both lists for these two terms. So here we have query X and Y. All right, I have these two. The first step, go to X's term entry in the dictionary, get its postings, right? The list of documents where X lives. We'll go to get Y from the dictionary, get its postings, and then we do the intersection. This will give us the results that contain both X and Y. So, how have we done this before when I've shown this example? The common sense version, right? Look at each item, every single pair of items in both sets. When they do match, add them to the list. If they don't match, ignore them. Okay, so 1 and 3, no. 2 and 3, no. 3 and 3, yep. 3 and 6. Okay, no. 1 and 5, 2 and 5, 3 and 5, 6 and 5. No, no, no. No, no, no. Yes. Okay, cool. We'll add 6. And finally 8 against all of them. Ta-da. Now, I've mentioned this a few times. This works. What's the problem? Wicked inefficient. Terribly inefficient. Because we're doing a lot of checks that, I mean, honestly, a lot of negative checks. There's going to be a lot of answers that are just no. But the problem is that we're not using anything in our arsenal to narrow this down, to speed this process up. We're just saying brute force. I will look at every pair and we'll write them down. That is an easy way to do it, and that is a way to do it. But remember, we need to think about optimizing. If we're walking towards, we won't ever get to Google, but if we're walking in that direction, we want to use the same kinds of efficiency that they have been using for years. So remember, we are always thinking about scaling up. So if I have to check which item shows up in both lists, comparing every single item in one list, so that's we start with big O of n with that. We're already running through one list. And now we got to compare against every item in the other list as well. Oh, so now we're comparing for each item in the list, we're doing a whole other list. Big O of n squared. Now, that's okay if our postings lists are 10 and 20 things long, if we have a small collection. But if we've got millions of IDs in each posting list, that's a lot of processing power. We're just kind of flushing down the toilet. So that's why we optimize. Because when we scale up, we need to think about how to keep things workable so they don't blow up in terms of the processing wasted. So again, this algorithm, it's very slow. For a list of length 4, there were 16 comparisons. Big O of n squared, not so good. It's not the worst it could be. It could always be exponential or something. But big O n squared is not where we would really like to be for something we're going to do as frequently as comparing these lists. Because remember, we're going to do this quite regularly, especially if we have 20, sometimes you search 15 terms at once, right? And making sure that all of the items are in all of the lists. Oof, that's a lot. So what's a better method? Well, I can tell you it's not super straightforward. This involves some clever engineering, and this happens to be why we want to make sure that our sets, our list of document IDs are in ascending order. So because they're sorted, we can implement a better, more efficient intersection algorithm. Let's talk about it. So we know that these postings are all sorted bottom to top by document ID. It actually wouldn't matter. They could be sorted in the opposite direction. As long as they're sorted in one direction or another, it matters. So we can cut out some of these comparisons, and I'll show you how. So consider this logic. As we're going through these lists, we'll start at the left, right? We would begin comparing the first entry for A and the first entry for B. First document ID for A, document ID for B. That's 1 and 3. We already can tell they don't match, but let's look at how we can proceed through this list in a way that exploits some of this sorting. So, if the IDs don't match, we advance the smaller ID. Now, why? Because any ID that's larger than the larger of these two IDs. So for A, for the very first one, 1 is the smaller ID, 3 is the larger ID. So any ID larger than the bigger one can't possibly match with the smaller one. So we wouldn't increase 3 to the next entry because the smaller one is already too small. We know that because they're sorted. So while we increase the smaller one, we might still hit 3. And in fact, looking ahead, we can see that we will hit 3. But so while comparing 1 and 3, it's a wasted comparison to make any more comparisons against 1, because we know that the very first document B appears in is the 3rd one. So we're not going to go and look for another comparison at the 5th one, the 6th one, 8th one, because 1 is already ruled out. Okay, so now if we hit a match, we record that match as we've done in the past, right? We say, oh, eventually we will get to 3 compares, and then we'll advance both IDs. We know that the current ID matched, and it can't happen again because it's not going to be listed multiple times. And so we move on. So both of them get to advance. What are we doing here? So let's run through this. First, we compare 1 and 3. That's not a match. Okay, we're not going to compare 1 against anything else in this second list because we know it's too small. It's off the left end. Okay, so we'll advance the top one. All right, check number 2. Cool. Number 3. Got it. Great. We will advance both of them now because we know 3 is not going to show up again. 6. Okay, so the 5th entry, not quite. Advance it up 1. Aha, another match. So, wait. Oop. Okay, give you a little bit of that in-person flubbing. So, the original was squared by brute force. The new one is in linear time thanks to our sorting. Linear time. We ran through, it took us a few chunks, right? 1, 2, 3, 4, 5 checks. That's a lot less than 15. And because we are always advancing upward, it might take us a little bit more than the length of one of these lists. But ultimately, this allows us to check through 2 lists, 2 sets of arbitrary size and length in linear time. And in fact, in quite good time sometimes, especially if one of the terms is short, has a smaller list. So let's do an example on our old friend, my cat document, right? So I have a cat. Her name is a little bit. She's not a graceful cat. She's sweet. Blah, blah, blah. So the queries are cat and is. So we'll pull out cat, 1, 3. We'll pull out is, 2, 3, 4. Let's do the real quick algorithm, right? 1 and 2. No, we'll advance the smaller one now, right? Because we know it could still hit 2. Oop, it doesn't. It hits 3. Okay, now we advance the smaller one again to 3. Okay, we see a match. We write that down. Oh, we fell off the end of the list. We're done. Document 3 is the only one between cat and is. We didn't have to compare everything. We did it in 3 comparisons. Let's do another on our old green eggs and hams. So we know these, not going to dwell on the text. So I, that appears in documents 2, 3, 5, and 6, and there appears in documents 4 and 5. So let's do this. Compare 2 and 4. Nope. 3 and 4. Nope. 5 and 4. No. Now we'll switch the other one. 5 and... Okay, got it. Oh, we fell off the end. 1, 2, 3, 4. You could also imagine you might even get shorter than one of the lists, right? If I had 5 more documents on it, we would have fallen off the end of there and we'd be done. No brute forcing, no multiplexing across the full length of both lists. We just get document 5 in 4 steps here. So, how do we write this algorithm? Ooh. So this will be the topic of one of the assignments later. It's all right. It's doable. It's step by step. And again, I'll show you exactly how to do it. But we'll talk about it because some of this course is understanding the nitty gritty. This is a key idea. This is noticing how all of the interlocking bits of this process fit together. So, I've mentioned the textbook before. We're gonna snip a bit of code from the textbook. Okay, so this is the intersection algorithm they espouse, and I think it's good. In fact, I can't think of a quicker way to do this. But we're going to walk through this. We're going to pull this code apart and look at it. Okay? So, top to bottom, we'll just do it really quick. This is a function named intersect, and it takes two lists of postings, P1 and P2. We set aside a space for the answer, and then we're going to do a loop. While both P1 and P2 are not falling off the end of the list, is what that means. So the pointers are actually looking at something. Then we're going to say if the document ID out of P1 is the same as the document ID in P2, then again, this is when we record our answer and we advance both pointers. P1 goes to the next, P2 goes to the next. Otherwise, if the document ID, so if they're not equal, then one of them has to be larger. So if document ID of P1 is larger, or is smaller than document ID of P2, then we'll advance P1 only. Otherwise, we'll advance P2. Eventually, as we've appended things to this answer, we get our short list of the intersected lists. So, again, not just the visual follow along, but I'll write it all out. Intersect takes two pointers, P1 and P2, and the idea of pointers is that these are where we are looking in the list right now. Typically, we're going to use integers when we do this ourselves, integers and arrays. But for now, it's just the general concept that we are pointing somewhere in the list, these pointers. We define an empty list to hold the result in line 1, right? In line 2, we start this loop that will end as soon as one of the pointers falls off the end of the list and is pointing at nothing, okay? So now what actually happens in the loop? Line 3, if the IDs are the same, then add that ID to our list and then advance both pointer 1 and pointer 2. Otherwise, so if they're not the same, one of them has to be larger. So if P1 is the smaller ID, then advance P1, right? We've talked about why that's useful. We're exploiting the fact that these lists are sorted. Otherwise, we advance P2 because it's smaller. Because by default, if P1 was not smaller and they're not equal, then P2 must be smaller. We do this over and over. We loop through parts through lines 2 through 9 over and over until our answer is full. One of the pointers falls off the end of the list for sure, and we have our answer. We have thoroughly checked the entire list. Okay, now we're going to do this again, but we're going to run an example. So let's do it. Here's the code again, and I'm going to show you a timeline of when things fire off, which lines fire off when. Okay, right at the start, we've got the pointers set up. They are looking at the postings lists for A and the postings list for B. The very first thing we do when this function fires is we set aside a little space to have our answer, right? So that's line 1. We did line 1, great. Now we'll do line 2. So the conditions of this loop are, as long as P1 is not nil and P2 is not nil, we will continue to do the loop. Nil in this case means the pointer is just no longer looking at anything. It will have fallen off the end of the list, right? So that, in this case, is good. We're good. We're going to keep going because these pointers are pointing at stuff. Cool. So that's good. What's our next check? Well, we want to check, is P1 pointing at a value that is the same as the value that P2 is pointing at. So P1 is looking at a 1, document 1. P2 is looking at document 3. So those are not the same. We will jump to line 7, right? Because this is the else of that if. So now the question is, which one's smaller? Is P1 smaller than P2? Yeah, in this case, P1's pointing at a 1, P2's pointing at a 3. So great, we will advance. Or that means that we will do the first line and not the other. So we advance P1. with line 8. Great. So we've executed the loop once. We're going to go back to the top. Okay. So again, both of our pointers are looking at something useful. Are they the same? No, they're still not the same. So we're going to go and check again. Okay, so if they're not the same, which one do we move? Again, P1 is still smaller than P2, so we will advance P1. Great. Back at the loop. We're still good. We're still looking at stuff. We're still looking at items, not the void. So are they the same? Yes, this time for once they are the same. So what do we do when they are the same? We add the answer, this item to the answer. So 3 gets added to the answer. And we're going to advance both P1 and P2. And now we're going to loop back. Okay. We're still both looking at stuff. Great. Now we're going to check again. Is 6 equal to 5? No. We will go down to the advance 1 segment. Is P1 smaller than P2? No, not this time. So instead of doing line 8, where we advance P1, we're going to do line 9, where we advance P2. Okay. So now we're going to jump back to the start of the loop. Are we looking at things? Yes, the answer is yes. So we're going to do, are they the same? Yes, they are the same. 6 and 6. Great. We're going to write that down in the answer slot. We're going to advance P1. We're going to advance P2. And then we're going to go back to the start of the loop. Finally, is P1 not nil? No, P1 is nil. P1 is nil. This loop ends. This is our answer. 3 and 6. We return the answer. Line 10 fires off. That's a whole lot of talk about one algorithm. But this is how you make a useful algorithm that, in one sense, is custom. For this exact purpose of comparing two lists, we need this kind of operation. It's a lot of steps, but remember, the goal of getting your head around these is that now when you actually go to fire off and say, hey, compare these two lists, it's going to do them in linear time, n length time, as opposed to n times n length time, n squared. So it's worth it. It's painful. It's worth it. And again, we'll walk through a way to implement this. It'll be a little bit different. We're not going to use this abstract pointer stuff. We'll just use index, integer indexes for arrays. So now thinking, we can do more complex queries, right? We can not just do one query at a time. We can compare A and B and C, right? Now remember, with the old way, we would have sort of the intervening results. That works the same way with these lists. So you resolve to process A and B and C, then we're going to have to process A and B first, or B and C, either way works, first, and then the whatever's left over and the result of that previous operation. So, as usual, we can just store that intermittent result and repeatedly do the intersection operation. So we just learned how intersect, the function, works. So temporarily store the intersection of A and B, and then we can take the intersection of that temp variable and C. All right, let's see it. So cat and is and she in our little list here. Cat, that's 1 and 3. Is, that's 2, 3, and 4. And she, that's 3 and 4. But we'll do cat and is first. So we run through our algorithm. No, yes, done. Intermittent list is just 3. Okay, so now we'll do 3 with she. That's just one check. It is correct. Still just document 3. Let's do it again on Dr. Seuss. So, them and I and their. Again, this is the idea of we can handle as many terms in the search query as we want. So them and I, we'll do that first. them 2, 4, 5, and 6, I 2, 3, 5, and 6. Okay, so here we go. Compare 2 and 2, great. Compare 4 and 3, no. Compare 4 and 5, no. Compare 5 and 5, yes. Compare 6 and 6, yes. So the documents that have them and I are, there's 3 of them, 2, 5, and 6. Great. So now we can do that with there. So there has 4 and 5. Here we go again. 2 and 4, no. 5 and 4, no. 5 and 5, yes. Hey, they're document 5. This is it. This is how we take our inverted index that we spent all of last time building up from the start, and queries, which, again, we are typically using a lot of anding in most queries, and we're able to now search for documents. So a note on how best to arrange this. So here we're taking 3 lists and we're chunking through them, right? The list for them, the list for I, and the list for there of the documents associated with those terms. There's a good way to arrange them. So the intersection algorithm is complete as soon as we reach the end of either list, remember. So how might we want to sort our equal operations? Well, intersections are strictly reductive. So the intermediate results can never be larger than either of the intersected lists. So the only way, the maximum is that both lists contain the exact same list of documents. So you end up with the exact same list. It's always shortening them. So, but remember that there's a sort of a transitive property here. I can arrange them in any way I want. So if I work on a list, say I have a word that has exactly, or a term that has exactly 1 document associated with it, I should probably search that first, right? That, compared to any other list, odds are good we're going to narrow down really fast. So whenever we're doing these big intersections of lots of things, we want to reduce this processing by do the small ones first, because they're the most eliminative. Let's look at an example. We got collections of magazines about pets, okay? We got dogs in these documents, cats in these documents, and capybara in just 1 document. Where would we start, right? If I was going to minimize processing time, if I'm going to do dog and cat, even though we've implemented this really nice intersection algorithm, it's still going to take a bunch of steps, right? 1 and 1, great. 2 and 2, great. 3 and 4, no. 4 and 4, great. If I just do capybara and dog, 6 and 1, no. 6 and 2, no. 6 and 3, no. 6 and 4, no. 6 and 6, yes, done. We fall off the end of the capybara list immediately. And now we know that there's only 1 document that contains dog and capybara. It's number 6. If we're going to now do that against cat, again, as soon as we advance that pointer, we're going to go 1, 2, 4, 5, 7. Oh, shoot, that's larger than 6. We're done again. So we found a way, but just by reordering things. Again, this is the beauty of sorting, helps us shortcut so many algorithms. So let's do another. Them and I, Sam I am. We'll start with the lowest frequency term. Sam I am happens in 1 document, them happens in 4, and I happens in 4 of them as well. Sam I am, I. We'll do that. I and them are the same length, so we'll just start here. Sam I am, good. We got it. Oh, we got it in 1. Okay, let's do it against them. We got it in 1 again. In exactly 2 steps, we have found the number of documents that are appropriate for this query. 2, compared to if we started with them and I, while still nicely linear, it's still a much longer case. So, to make good use of this, just a note, just, keep in the back of your mind, Boolean distributive laws, those exist just like algebra has distributive laws, right? You can flatten out complex queries before you start sorting them. You can only sort within the same kinds of operations, because you don't want to end up screwing something up where you meant to AND something where it was supposed to be ORed or whatever. So we can apply these same laws. So the law for OR would be A and B or C is the same as A and B or A and C. You distribute it through the parentheses. The distributive law for AND is the inverse here. So A or B and C is the same as A or B and A or C. Okay. Just a note. This is a point of reference. Don't memorize this right now. It would be useful to know these things. There might be a quiz question on it. There might not be. We'll see. But this is something to come back to. This is not something to stress about memorizing. So, review. The simple Boolean operations that were available to us when we were using a term document incidence matrix are not available when we're using these kind of squishy, sparse lists. They're still optimal in so many other ways, so we needed to find a way to reduce the complexity of these operations. So we've implemented an algorithm that takes ideas from set theory. We accomplished set theory operations like intersection. And I can tell you right now that the union version is very similar to it. And this is all to efficiently find the overlap between the postings lists, right? Sorting has helped us short circuit a lot of this processing. And we save just a lot of time in general, but we can go one step further and save even more time by starting all of our multi-complex operations here with the shortest lists. So short lists first, and also make sure they're sorted so that we can run through them in linear time. We have reached something that's quite efficient, whereas we might not have before. So that is how this fits together. And to look again at where that fits into the overall situation, well, remember we've got this inverted index to help us look for things in our big collection, and we've now introduced the idea of this is how we process our queries using set theory and efficient algorithms. Final thought. Where else might sorting things beforehand help you short-circuit tedious everyday tasks? All right, take care.